Hello dear students. So far we have learnt various scientific discoveries done by scientists to find the structure of atom, in which basically J.J. Thomson and Rutherford come to a picture. Now before we move ahead, let us learn a little more about the atomic number and mass number. We have learnt about these concepts in our previous classes. Now that you have entered the discipline of chemistry, we need to recall and revisit what all topics we have learnt earlier. So here, as we know that the positively charged particles and the negatively charged particles are there in the atom, let us see how they count for the atomic number and mass number of the atom. The presence of positive charge on the nucleus is due to the protons in the nucleus. As established earlier, the charge on the proton is equal but opposite to that of electron. The number of protons present in the nucleus is equal to the atomic number represented by Z. For example, the number of protons in the hydrogen nucleus is 1. In sodium atom, it is 11. Therefore, their atomic numbers are respectively 1 for hydrogen and 11 for sodium. In order to keep the electrical neutrality, for example, the number of electrons in hydrogen atom and sodium atom are 1 and 11 respectively. So, the atomic number Z is equal to number of protons in the nucleus of an atom or number of electrons in a neutral atom. While the positive charge of the nucleus is due to protons, the mass of the nucleus is due to protons and neutrons. As discussed earlier, protons and neutrons present in the nucleus are collectively known as nucleons. The total number of nucleons is termed as mass number of the atom. Mass number represented by capital A is equal to number of protons Z plus the number of neutrons small n inside the nucleus. Now that we have learnt about A, the mass number, and Z, the atomic number, let us understand the composition of isobars and isotopes. The composition of any atom can be represented by using the normal element symbol as X with a superscript on the left hand side as the atomic mass number and subscript Z on the left hand side as the atomic number. So, AXZ becomes the basis of representation of an element. Isobars are the atoms with the same mass number but different atomic number. For example, 14C6 and 14N7 are isobars. Here the mass number of carbon is 14 as well as nitrogen also is 14, but the atomic number we know of carbon is 6 whereas that of nitrogen is 7. On the other hand, atoms with identical atomic number but different mass number are known as isotopes. In other words, the difference between the isotopes is due to the presence of different number of neutrons present in the nucleus. For example, considering that of hydrogen atom, 99.985% of hydrogen atoms contain only one proton. This isotope is called protium or 1H1. The rest of the percentage of hydrogen atoms contain two other isotopes. The one containing one proton and one neutron is called deuterium, that is 2D1, and its percentage is 0.015%, and the other one possessing one proton and two neutrons is called tritium, 3T1. The third isotope of hydrogen is found in trace amounts on the earth. So, have a look on the screen. The three isotopes of hydrogen, 1H1, 2d1 and 3t1 are there on the earth, but their percentages are different. Other examples of commonly occurring isotopes are that of carbon. Carbon atoms containing 6, 7 and 8 neutrons besides 6 protons. Let us come back. Carbon has atomic number 6. So, obviously, whenever we say carbon, all the carbon atoms have to have 6 protons. So, what can be different? The difference can be in the number of neutrons that are present in the nucleus, and that is how it makes the different isotopes. So, the 3 isotopes of carbon, as you can see on the screen, are 12C6, 13C6 and 14C6. Chlorine atoms containing 18 and 20 neutrons besides 17 protons also make the type of isotopes. So, 35Cl17 and 37Cl17 are the 2 isotopes of chlorine. Lastly, an important point to mention regarding isotopes is that the chemical properties of atoms are same. You know why? You know that chemical properties are controlled by the number of electrons, and number of electrons is to be equal to the number of protons that are there inside the nucleus. Number of neutrons present in the nucleus have a very little effect on the chemical properties of an element. Therefore, all the types of isotopes of a given element show similar chemical behavior. So, my dear students, you have already learned about the Rutherford's nuclear model of an atom, which is like a small scale solar system, with the nucleus playing the role of the massive sun and the electrons being similar to the lighter planets. When classical mechanics is applied to the solar system, it shows that the planets describe a well-defined orbit around the sun. The gravitational force between the planet is given by the expression G is into m1 m2 divided by r2, where m1 and m2 are the masses of the 2 objects which are attracting each other by gravitational force, and r is the distance of separation of the 2 masses. The G is the gravitational constant. So, my dear students, you must have learnt in your physics class about Newton's law of motion. The classical mechanics draws from the Newton's law of motion, and it is applicable to the macroscopic objects. So, what was Rutherford trying to say? That as the Newton's law, the classical mechanics is applicable to the solar system, in the similar manner, he is suggesting that this property of attraction between the masses when separated by a distance is applicable to his nucleus and the electrons. The classical mechanical theory can also calculate precisely the planetary orbits, and these are in agreement with the experimental measurements. The similarity between the solar system and the nuclear model suggests that electrons should move around the nucleus in well-defined orbits like the planets. Further, the Coulomb force, that is K Q1 Q2 divided by R square, where Q1 and Q2 are the charges and R is the distance of separation of the charges. K is the proportionality constant. So, this between the electron and the nucleus is mathematically similar to the gravitational force. However, when a body is moving in an orbit, it undergoes acceleration if it is moving with a constant speed in an orbit because of changing direction. So, an electron in the nuclear model describing planet-like orbits is under acceleration. According to the electromagnetic theory of Maxwell, charged particles when accelerated should emit electromagnetic radiations. This feature does not exist for the planets because planets are uncharged. So, my dear students, let me just complete it again. Rutherford is saying that the nuclear model is like the solar system. Solar system consists of uncharged bodies, that is sun and the planets. So, here the scientists are saying that the uncharged body and the charged body are not in the same manner. Maxwell was working on the charged particles in his laboratory, and he says that when a charged particle like an electron is moving around another charged particle, oppositely charged particle, it should accelerate and also lose energy while it is doing it. So, if we visualize this, an electron which is moving in an orbit around the positively charged proton should emit radiations, and as it emits radiations, it will take a spiral path and collapse into the nucleus, isn't it? So, therefore, an electron in an orbit will emit radiation. The energy carried by the radiation will come from the electronic motion. The orbit will thus continue to shrink, as I just said, that it will take a spiral path. So, that means the stability of the Rutherford's model is at stake. The calculations show that it should take an electron only 10 raised to the power minus 8 seconds to take a spiral and merge into the nucleus. But this does not exist. This does not happen. The atoms are stable. This was a contradiction to the Rutherford's model, and thus the Rutherford model could not explain the stability of an atom. If the motion of an electron is described on the basis of the classical mechanics and electromagnetic theory, the Rutherford model does not specify it. You may ask that since the motion of electrons in orbits is leading to the instability of the atom, then why not consider electrons as stationary around the nucleus? If the electrons were stationary, the electrostatic forces of attraction between the dense nucleus and the small electrons would pull the electrons, and again the electrons would merge into the nucleus. So, my dear students, the experiments that were happening at the Rutherford's lab, then at the Maxwell labs, all together brought us to the developments leading to the Bohr's model of an atom. Bohr's model you have studied a little bit in your previous classes. Let us understand it better. Historically, results observed from the studies of interaction of radiation with matter have provided immense information regarding the structure of atoms and molecules. Niels Bohr utilized these results to improve upon the model proposed by Rutherford. The two developments played a major role in the formulation of Bohr's model of an atom. These were the dual character of electromagnetic radiations, which means that radiations possess both wave and particle-like properties, and other was the experimental results regarding atomic spectra. So, to understand how Bohr reached his model of an atom, we will discuss about the dual nature of electromagnetic radiations and the atomic spectra, so that we are able to understand the whole concept as Bohr saw it. The Rutherford's model, the Maxwell's observation, the electromagnetic radiation experimentations and the atomic spectra. All these put together will come to the Bohr's model. So, my dear friends, till now we have learnt how to calculate atomic number and mass number using given data. We can even identify and classify the given unknown elements as isotopes or isobars. So far, we have discussed the drawbacks of Rutherford's model, and now it was the time for the scientists to give a new model of an atom. The problem, as we discussed earlier, was that electrons which are moving fast release electromagnetic radiations. So, before we move into the new model of the atom, let us understand about various experiments that were happening on the electromagnetic radiations so that they can be combined into the nature of electrons that are moving around. So, in the mid-19th century, the physicists actively studied absorption and emission of radiation by heated objects. These are called thermal radiations. They tried to find out what are these thermal radiations made up of. It is now a well-known fact that thermal radiations consist of electromagnetic waves of various frequencies or wavelengths. It is based on a number of modern concepts which were unknown in the mid-19th century. First active study of thermal radiation laws occurred in 1850, and the theory of electromagnetic waves and the emission of such waves by accelerating charged particles was developed by James Maxwell in 1870. Maxwell was the first to give a comprehensive explanation about the interaction between the charged bodies, the behavior of electrical and magnetic fields on macroscopic level. He suggested that when electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. Can you relate it to the electrons? Electrons were moving fast. As they are accelerating, they would produce alternate electrical and magnetic fields. These fields are transmitted in the form of waves called electromagnetic waves or electromagnetic radiations. Light is the form of radiation known from early days, and speculations about its nature dates back to remote ancient times. In earlier days, that is during the times of Newton, light was supposed to be made up of particles, and it is called as corpuscular theories. The bundles or packets, corpuscles, it was only in 19th century when wave nature of light was established. Maxwell was again the first to reveal that light waves are associated with oscillating electric and magnetic character. Although electromagnetic wave motion is complex in nature, we will consider only a few simple properties of electromagnetic radiation. The first one, the oscillating electric and magnetic fields produced by the oscillating particles are perpendicular to each other. That means, if electric field is moving in the x direction, the magnetic field would be in the y direction. So, they are perpendicular to each other. And the second is, like unlike sound waves or the waves produced in water, electromagnetic waves do not require a medium and can move in vacuum. Why did we say that? You know that sound waves require medium to travel. You have learnt about the compressions and rarefactions. So, these electromagnetic radiations do not need any medium. You also know that when the light travels from the sun to the earth, there is a vacuum in between, there is no medium. So, even then the sun's radiations are able to come to the earth. The third one is, it is now a well established that there are many types of electromagnetic radiations which differ from each other in wavelength or frequency. These constitute what is called as electromagnetic spectrum. So, all the electromagnetic radiations move with the same velocity c, but they have different wavelengths and frequencies. The different regions of the spectrum are identified by different names. Some examples are radio frequency region. Do you listen to radio? The frequency is around 10 raised to the power 6 Hz, which is used for broadcasting. The microwaves, which are used in the microwave that we have at home or used in the radars, the microwave region is around 10 raised to the power 10 Hz. The infrared region is around 10 raised to the power 13 Hertz, which is used for heating. The ultraviolet region is around 10 raised to the power 16 Hertz, a component of sun's radiation. The small portion around 10 raised to the power 15 Hertz is what is ordinarily called as visible light. So, the visible region is only that small part of 10 raised to the power 15 Hertz approximate. It is only this part which our eyes can see or detect. Special instruments are required to detect the non-visible radiation, that is the infrared and the ultraviolet. And beyond that, different kinds of units are used to represent electromagnetic radiations. These radiations are characterized by the properties, namely frequency represented by nu and wavelength, that is lambda. The SI units for frequency nu is Hertz, or we can say second inverse after Hendrik Hertz. It is defined as the number of waves that can pass a given point in 1 second. You must have learnt about this in your physics class too. The wavelength should have the units of length. As you know that the SI unit of length is meter, since electromagnetic radiations consist of different kinds of waves of much smaller wavelengths, the smaller units are used. Have a look at different types of electromagnetic radiations on the screen. These differ from one another in wavelengths and frequencies. In vacuum, all types of electromagnetic radiations, regardless of wavelength, travel at the same speed, that is 3 into 10 raised to the power 8 meters per second. This is called the speed of light and is given the symbol c. The frequency nu, the wavelength lambda and the velocity c of the light are related by the equation velocity is equal to nu into lambda, that is velocity is equal to frequency into wavelength. The other commonly used quantity, especially in spectroscopy, is wave number. Wave number is represented by nu bar, a bar over the sign nu. It is defined as the number of wavelengths per unit length. Its units are reciprocal of wavelength unit, that is meter inverse. However, commonly used unit for wave number is centimeter inverse. Obviously, this is not a SI unit. Now that we have learned so much about the electromagnetic radiations, it is time for some task. I am giving you a problem which is coming up on the screen. The Vivid Bharati station of All India Radio Delhi broadcasts on a frequency of 1368 kilohertz. So, what have we given you? We have given you the frequency. Calculate the wavelength of the electromagnetic radiation emitted by the transmitter. Which part of the electromagnetic spectrum does it belong to? So, there are two questions in the same problem. And before we solving this problem, my dear students, we have to collate all the data that is available to us. What are they asking us to calculate? Wavelength, that is the lambda. Okay. And what have they given us? They have given us nu, that is the frequency. Now, we know the formula that lambda is equal to c by nu, where c is the speed of the electromagnetic radiation. So, you have to bring in this value yourself. It won't be given in the question. 3 into 10 raised to the power 8 meters per second. So, whenever there is a question of electromagnetic radiations, you should know c would be 3 into 10 raised to the power 8 meters per second, okay, which is the speed in the vacuum, and nu is the frequency which has been given to you. We have to substitute the values, but there is a problem. The frequency has been given in kilohertz, 1368 kilohertz. So, my dear students, this is the crux of solving numerical problems. Always remember, to convert the units to a compatible unit form. Okay? So, here because we have taken c, that is the velocity in meters per second. So, here the frequency also should be in per second. So, it comes out to be 1368 into 10 raised to the power second inverse. On substituting the values, which I leave to you, you will get lambda as 219.3 meters. So, my dear students, we have to learn this life skill from the scientists, that collaborate and learn from each other. Happy learning.